Welcome, aliens, to planet Earth. Because our planet will most likely look a lot different than yours, you might be wondering, how is it shaped, and especially by energy? I'm going to get to that very soon, but first, it'll be worthwhile to know that energy greatly shapes the atmosphere, surface, and interior of our planet. First, let's talk about the atmosphere. You might be wondering, what is this atmosphere, and what does it do? Well, it protects us from radiation and asteroids, provides us with gases to sustain life, and helps moderate temperature. Our atmosphere reflects 30% and absorbs 20% of the sun's radiation, protecting us from half of it. A very important part in the atmosphere is the ozone layer, as it absorbs the solar radiation and turns it into heat. Our atmosphere comprises of roughly 78% nitrogen, 21% oxygen, and 1% everything else, including carbon dioxide and water vapor. On planet Earth, carbon dioxide and oxygen help both the plants and the animals survive. Our atmosphere also facilitates the greenhouse effect, which keeps most of the heat on the surface of our planet. Speaking of heat, the three main regions of the Earth, the polar, temperate, and tropical, all are heated differently because of how they're aligned in relation to the sun's rays. The closer you are to the equator, which is the central line on our planet, the more direct sunlight you get, and as a result, it's usually more warm. Also, because our planet is tilted to the side, we have these things called seasons. Depending on where the Earth is on its revolution around the sun, different areas of Earth will get different amounts of sunlight. The four positions pictured above are very important in relation to the seasons. The solstice is when either the north or south half of our planet gets the most sun during the day of all of the days of the year. The equinox is the exact opposite. It's when the day and the night are equal in length. On a slightly different but related note, what is wind? Wind is the movement of air from high pressure areas to low pressure areas. For example, when the ground heats up, the air above the ground rises and results in lower pressure. Then, the high pressure from the surrounding area flows into the low pressure, creating wind. There are two types of wind, global and local. Local winds happen on a small scale and usually change direction based on if it's daytime or nighttime. During the daytime, the land is hotter than the water, and thus wind flows from the ocean or sea towards the land. Contrarily, at nighttime, the water is warmer than the land, and thus wind flows from the land towards the ocean or the sea. Global winds, on the other hand, are caused by large heating differences on the surface of the Earth, like what I talked about previously. For example, a Hadley cell is a type of convection cell that goes from 0 to 30 degrees in both directions. Because the equator is the hottest, the air rises from the equator and flows out away from the equator. Then it settles down and then flows back towards the equator because of the high and low pressure differences. Water and weather. The water cycle is a cycle in which water evaporates, condensates, and then precipitates. In a nutshell, the water is heated up, it rises, but because temperatures drop as you rise in altitude, it condensates and becomes cloud. When the cloud is too heavy, the water is drawn down by gravity and it starts to precipitate. Precipitation is what most of us humans think when we hear weather. When water droplets are drawn down by gravity, it becomes rain. When ice crystals are drawn down by gravity, it becomes snow. Hail, which are large ice crystals, are formed when small ice crystals bounce around in a cloud and gain mass until it becomes too heavy and then they're forced to fall. Sleet is when rain freezes as it falls, and freezing rain is what happens when the rain freezes when it hits the surface. Now let's go a little bit deeper and see what really causes this weather. An air mass is a large mass of air that retains uniform physical characteristics. When two different air masses meet, they don't mix. Instead, they create a boundary, which is called a front. A cold front is when a cold air mass overtakes a warm air mass, and the warm front is when a warm air mass takes over a cold air mass. Usually, warm fronts are a lot less steep than cold fronts, and cold fronts usually cause a lot more bad weather. Going on to a different topic are cyclones and anticyclones. These are simply rotating masses of air that have either high or low pressure centers. In the northern hemisphere, because of the Coriolis effect, a cyclone rotates counterclockwise and an anticyclone rotates clockwise. Now, let's stop talking about the atmosphere and go into the surface. First of all, what is erosion? Erosion is the process of the surface of the Earth being worn down. Weathering is a type of erosion, and there are two types of weathering, chemical and mechanical. Mechanical occurs because of physical wear and tear, whereas chemical occurs because of chemicals breaking down the rock. Erosion can sometimes cause mass movement, which are downwards movements of dirt and rock. Slumping is a type of mass movement. It occurs when a large mass of dirt and rock slides down a hill as one unit. Fresh water can also erode things in the form of rivers and streams. For example, over time, meanders occur in rivers because of small disturbances that are exaggerated by the erosion. Wind is another type of erosion, and there are two main types of wind erosion: abrasion and deflation. Abrasion occurs when sand is blasted at rocks, wearing them down. Deflation is when wind carries away small particles of sand, leaving only larger rocks. Finally, ocean waves and currents can also erode things in the form of hydraulic action and abrasion. Hydraulic action is when cracks in a rock are repeatedly pounded into with water and air, whereas abrasion is when waves carry away loose sediment. Waves can also shape the surface of the Earth through longshore drift, which brings sediment up a coastline. This occurs because one wave goes into a coast and brings out the sediment, but then another, stronger wave pushes the sediment back. This occurs repeatedly. Finally, the interior of the Earth. What is it made of? Well, the crust and mantle are made up of mostly silicates, which are rocks that contain silicon and oxygen. An elemental analysis of the crust reveals almost half of it is oxygen. Over a quarter is silicon, and the most abundant metal is aluminum. The outer core is made out of both iron and iron nickel alloy, but the inner core is made out of pure iron. While we're talking about iron, let's talk about rocks and minerals. Rocks are simply combinations of minerals, and minerals are inorganic solids that are made up of one chemical compound and arranged in a crystalline structure. There are plenty of differences between rocks and minerals. For example, minerals have a definite chemical compound, whereas rocks don't. Additionally, minerals usually have some certain shape, whereas rocks don't either. However, minerals cannot be organic, however, rocks can. There are three different types of rocks: metamorphic, igneous, and sedimentary. Metamorphic rocks form under high heat and pressure. Igneous rocks form when magma cools, either above or below the surface. Sedimentary rocks form when sediment comes together. This is a good graph that roughly shows how rocks are created. As you can see, energy, either from the sun or from the earth, always helps in building rocks. Sedimentary rocks are usually always formed by either wind or fresh water. As you may remember, both of these are very directly connected with energy. On the other hand, igneous and metamorphic rocks are formed from the energy from the earth, either from the cooling down of the core or the decay of the isotopes in this crust. While talking about the layers of the Earth, both Earth's atmosphere, the Sun's convection zone, and the Earth's mantle experience convection. In the mantle, hot rock rises after being heated by the core, and then sinks after being cooled. The tops of these convection cells are what move the plates, and and thus substantiating the theory of plate tectonics. For example, when two of these convection cells are right next to each other and turn opposite directions, they create diverging borders, which in turn, if they are formed in the ocean, form mid-ocean ridges. Now that I've mentioned plate tectonics, let's talk a little bit about it before we go into the next section. Plate tectonics is a theory that all these plates, which form our continents and our oceans, are all suspended on the asthenosphere, which is a thick liquid. These plates are always moving and form the geological features that we know today, such as volcanoes and mountains. The theory of plate tectonics hypothesizes that plates subduct and come out from plate boundaries. For example, at the mid-ocean ridges, new plate is formed. On the other side of the plate, the old crust subducts and goes back into the mantle where it becomes magma. On a very related note, earthquakes are sudden movements in the plates. For example, when a plate gets snagged, it will slowly build up stress until the stress is too much for the rock to handle, and then the rock breaks, releasing all the pent-up energy. A small portion of the energy released is released as seismic waves, and using these seismic waves we can find out more about the Earth's interior.